Right. Welcome again for yet another experiment. What we are going to do today is to see the effect of ions on the CMC of the detergent. Now, detergent, as you would know already, is extremely important in our day-to-day life, like as essential as washing our clothes, right? And the critical micellar concentration is extremely important, right? In all the systems like refinery and everywhere, these detergents are going to play a very important role. Okay, now what is this CMC all about? It's called as the critical micellar concentration. Now, to understand that CMC, we have to first understand a detergent molecule. Now, what is a detergent molecule? Just give me a sec. Any detergent molecule will have a polar head, which is drawn over here, and will have a hydrophobic tail. Right? This is how the detergent looks like. Now, this polar head can be negatively charged or positively charged. Let's write it down. Now, this can be positive or negative in nature. Both are polar, but the hydrophobic long tail remains in both the cases. Okay, now we are going to measure the CMC using conductivity method, conductometer. Now, how we are going to do it? Let's draw a small graph for it. Have the detergent concentration on the x-axis. There you go. And the conductivity on the y-axis. Conductance or conductivity, whatever you would like to call. Now, as this is a polar head, when you put in water, right? Because of this polar head, when you keep increasing the concentration, the conductivity of the water increases. Okay. Now, what happens at the CMC, critical micellar concentration? These polar heads, they come together to form micelle. How the micelle look like? It looks like all the polar parts are outside and all the hydrophobics are inside. Right? Now they become more bulky in nature. Now, because of that bulk, the mobility of the ions, the conductivity decreases, and you see a kink, right? A kink. So the conductivity would increase as you increase the concentration, but that increase is not as steep as it was before. There you go, something of that sort. Now, what do you do next? You draw tangents, like here on this side and like there. At the intersection of the two, you draw a perpendicular on the concentration axis, and that's how you define the critical micellar concentration, CMC. Okay, now this CMC can be perturbed by changing the polarity, right, of the solvent system. Now, how do you do the change? What we are going to do today, we are going to see the effect of ions onto this critical micellar concentration. Now, what kind of ions we are talking about? We are talking about some the detergents, the ions we will see that effect onto detergents like SDS, right? So what is our SDS? So you have a sulfate group over there. There you go, and it's a negative charge over here, and counterbalanced by sodium. So SDS, it is S for sodium and another S for sulfate. So that's taken care. Now, what is D? It's a right? So you have a hydrophobic chain which is like 12 carbon long, 12 carbon atom long. That's your hydrophobic chain. Okay, this is what is SDS all about. Good. Now this SDS is negatively charged. The polar head is negatively charged in this case. As you would see, it's counterbalanced by the positive sodium. Now the other detergent is CTAB. Right? Now what's our CTAB? It is ammonium bromide. Right? TAB. TAB is tri-ammonium bromide. So of course we have to draw an ammonium ion. Right? Now the charge on the ammonium ion will be plus, counterbalanced by bromide, and the hydrophobic chain, which is 16 carbon atom long. Right? Now this 16 carbon atom is cetyl. Right? Cetyl. Right? So it is cetyl is C, TAB is tri-ammonium bromide. That's CTAB for you. But the charge over here, as you would see, it's the polar head is positively charged, counterbalanced by bromine. Right? So this, our SDS, the polar head is negatively charged, and for our CTAB it is positively charged. Okay, now what else do we have? We have again a non-ionic detergent which has a polar part but is neither positively charged or negatively charged, which is twin 80 in this case. Now what kind of detergent it is? It is a non-ionic detergent. Let me write it down. It is a non-ionic detergent. Right, there you go. Fine, but the structure is very complicated for me to write upon the board. So Rupesh, can you just zoom in? So you would see this is all the oxygen part is the polar part, and the R, what you see on the left, is the hydrophobic part. Right, it's the hydrophobic bit. So we have SDS, CTAB, and twin 80. Right, these are the three detergents for which we will be studying the effect of ions on these three different kinds of detergent: positively charged, negatively charged, and the non-ionic detergent. Now what kind of ions we are going to study? Right, we are going to study different kinds of ions effect, and also the change in the polarity of the solvent by using hydrophobic solvent maybe. Okay, so now let's see, if you change the polarity, how does the CMC changes. Right, so now what we are going to do, we are going to have different kinds of ions. Let me rub it off so that I have some space to write. So we have some positive ions. What positive ions? Right, oh, okay, it's too big. Let me write again. So positive ions. So what kind of positive ions we are going to study? We will write. Also we will have some negative ions, anions, and we are going to have some hydrophobic solvents, which we are going to study the effect. Non-ionic, I'm writing, but it's hydrophobic. So the first is sodium chloride, the second one is potassium chloride, the third one is calcium chloride, and the fourth one will be the magnesium chloride. Right, now as you would notice, all the ions in these four salts are the same. So any effect will be the virtue of these positive ions, whether it is monovalent or divalent in nature. Right. Now likewise for the anions, we are going to have sodium chloride again. This is the common salt for both the studies. This second one will be sodium hydrogen phosphate, right? The third one will be sodium nitrite, right? And the last one will be sodium carbonate. Right, there it is. Okay, now you would have noticed you have the positive part is the same, so any change in effect in the CMC will be by virtue of the anions. Okay, now for the non-ionic or the hydrophobic solvent, what do we have? We will have 3 different solvents which we will be testing. Now what those solvents would be? The first one will be DMA. That's a D. Yeah, that's an A. Okay, that's a dimethylamine. The next one will be DMF, dimethyl formamide, and the third one will be, oh, my phone rings. My apologies, I forgot to put it on silent, so I kept it on flight mode. It won't bother us anymore. Okay, let's continue. So the DMSO is the third solvent what we are going to test. So they are the hydrophobic solvents. We will study their effect onto the CMC for the 3 different detergents what we have, the STS, yeah, CTAB and 2 in 20, and we will also see the different effects of these ions. Alright, there it is. Okay, so these hydrophobic interactions we will do it at the CMC, which we already find out as a control for the metal ions, and then we'll see how these solvents affect the CMC value. Okay, yeah. Now we have in nutshell some positive ions, cations, anions, and some hydrophobic solvents for the effect we are going to see on the 3 different detergents what we have got for you today. Okay, so these are the negative ions and these are the hydrophobic solvents, 3. Now for doing all of these experiments I need a help, a team, right? So I have a team with me, so Sonali is going to help me with the experiments today. So there it is, Sonali, and there is Rupesh, my henchman, for helping me with the recording. There it is, Abhijit sitting over there, and there Sandesh. And it's all about a teamwork. Without a teamwork we cannot do any of these experiments, right? Now let's begin. Let's go to the experiment bench and see how things are to be done, right? So here we are. Now Rupesh, can you please come on that side so that the recording is better, right? So this is our simple setup for today's experiment. So we have this conductometer. It's a pocket conductometer which you dip in a solution and the digital display will be seen over there on the screen, right? Then we have this distilled water. Now this is like one of the experiments we are going to do for the demo purpose, right? But all the other data has already been done for you. Okay, so we are going to find the CMC for STS today, right? And then we are going to see the critical micellar concentration by titrating in. Right. Okay. Now what we are going to do for the salt effect, our reaction volume for all the experiments will be 50 milliliters, right? And then to this we are going to add like 200 ppm of any salt, and then we are going to titrate in our detergent, which is 0.05 molar, all the concentrations, and we are going to add 1 ml at a time, and we are going to go up to 15 milliliters, and every milliliter we add in, we are going to measure the conductance. It's a very simple experiment, not complicated at all, right? And then we will see if at all any of those ions which we had added, does it shift the CMC value for those detergents, the 3 detergents which we are going to see. Okay, let's begin. Now what we are going to do, we are going to start off with our conductometer. We will be putting it in water, right? There it is. So we put it in water, nice, and rinse. And if you would see the display, there is almost no conductivity over here. Can you zoom in, Rupesh, here? So it's almost no conductivity. It says only 2 units, right? Now that's our water here, on which we will be that's our experimental beaker. First we will be cleaning our probe. It's nice and clean, right? There it is, dry. And then we will drop it in in water. This is like distilled water for the CMC experiment, what is being written. And if you would see, there is no conductivity here, right? And then as Sonali is going to add SDS, I will note down the readings, right? So the first reading without any additions, it says 1, and we are going to keep our probe all the time into the solution from thereafter, right? Once we put in, we won't take it out, right? Okay, so we are good to go. So the probe goes into the water. That's our, over here. Let's check the reading again. We leave it over there, take the SDS solution, right? The 0.05 molar solution, and we are going to add 1 ml at a time, right? Here it is. Can you show it's set, the pipette has been set in 1 milliliter? Yes, there goes the first ml into the solution, right? We shake it a bit with the probe, mix it with the probe itself, there it is, and then we measure the reading. So it says 65 units, right? 65 units. I'll make a note. Okay, so there goes the second milliliter. So if you would see the difference between first and the second reading, 65, there goes the second milliliter, and the value is, let's let it stabilize. It says 122. Yeah, that's what it is. I am noting down 122. Now let's move on with the third milliliter into the system. Let's move on with the third milliliter. Yes, there it goes, right? And the mix it, and the reading says as 185, right? 185. Yes, and that's the note I had made. If you would see from the first to second, it is 1 to 65 to 122 to 185. 60, almost 60 unit difference. There goes the fourth ml, and then it is 130. Sorry, that's 232. Not 132. It's 232. Okay. There it's the need again, it's almost a 60 unit difference. Yeah, slightly less, but should be all right. So there comes the 5th milliliter. It gives me the value of 280. 280. Let's make a note of it. Now if you would see from the first, it was the jump of 60 units, and now it has slowly slowed down. The increase had slowed down the jumps, right? Now there goes the next milliliter, the 6th milliliter, and the value is 320. Yeah, as you can observe that still on addition of the detergent the value is increasing, but not that steep as it was before. In goes the next milliliter, the 7th milliliter, and the value is 355, right? Okay, 355. It's an art to read that conductometer upside down. I'm trying to read it. So far I'm managing it. It's good. The next 8 milliliter in all so far, it is 389. Yeah. Okay. Is it? Yeah, stabilizing a bit, but yeah, it is kind of stabilizing at 389. You have to allow the system to stabilize a bit because it fluctuates. Anyway, I'm making a note of 389. Okay, there it goes, and in goes the next ml. All right, mix it a bit. Right, and the value is 422. Okay, so it is slowly rising now. Initially it was like big jumps, now it is slowly rising. So then the next reading would be 445, right? Yeah, it's quite linear in nature, but less steeper than before. So we already had passed the CMC mark, right? So if you plot the graph and see, you will see a nice kink in the graph, right? And 474. Okay, then the next one we are adding again. Right, is 498. Okay, there it goes. In goes the 13th milliliter. Now these all experiments are for demo purpose, so these readings will be different from what we will be providing you. Yeah, the next reading is 521. Yeah, 521. Now the other readings, as I said, the water also has been measured along with the other ions. Yeah, and then we will be using those readings for our calculations. But yeah, by all the means you can use this. That's 540, right? And the last ml, the 15th ml, has to go in now. So in goes the 15th ml. You stir it a bit, yeah, and measure the reading, right? It is 563. right? Now these are the readings what we have got. Can you zoom in, Rupesh, so that everybody can see? Yeah, these are the readings for the 15 milliliter what we had added, but these are the readings what we had used for the demo purpose, so they might vary compared to what we are going to share as the raw data with you, right? Now what we had done already for you, right? So we had already done the positively charged ion effect, the cation effect onto this system. So that's your distilled water, that's your magnesium chloride distilled water beaker over here, the control system, right? Then goes your sodium chloride, then goes your potassium chloride and calcium chloride over here, the cationic effect, right? Can you see NaCl, right? Now here we are the setup experiments what we had done for the anionic effect. The sodium chloride is the common bit, as you would have noticed, yeah, for both the cation and anion. So that's why you will see the 3 rows in the anion effect. So what all things we have in anion effect, right? Sodium hydrogen phosphate, right? Oh, this hydrogen should be like Na2HPO4, right? And then sodium carbonate. Oh, the carbonate is written twice, so one should be the nitrate over here, the sodium nitrate, right? So let's see the beaker. That there you go, the nitrate I was talking about. Okay, and there the carbonate and the hydrogen phosphate over here, right? Likewise, we had also done seen the experiments for seeing the hydrophobic solvents like dimethylamine, dimethylformamide, and DMSO. So those experiments had already been done. All of these experiments have been done together, so that's why the control makes more sense. But by no ways I am going to stop you from plotting the experiment what we had done now. Now what is more important for these experiments is to really understand how things are working over here, the effect of metal ions and the solvent onto the CMC, right? It is very those kind of metal ions are like positively charged metal ions, cations, anions, and hydrophobic solvents. Now if you would see experiment wise, it's not a very complicated thing, right? We had done it right away. It's not a very complicated thing, but the whole thing boils down to the data analysis what we have provided, right?